In neurons with myelinated axons, the action potential is able to travel along the axon at a much faster rate than in unmyelinated axons. To give you a sense of how much faster, unmyelinated axons, the action potential travels anywhere from 0.1 to 10 meters per second, which is like 1 mile an hour to 20 miles an hour. In a myelinated axon, the action potential can go as high as 150 meters per second, which is approximately 330 miles per hour. So much faster than in an unmyelinated axon. Now, how does it work? It uses something called saltatory conduction. Saltatory conduction means that it jumps. It comes from the word salta, which means to jump. And this is how it works. So I've drawn an axon here, and around the axon you see places that have been wrapped in myelin. Recall that myelin, the myelin sheath, is produced by either Schwann cells or oligodendrocytes, depending on whether you're in the peripheral or the central nervous system. Now, in these regions, which are called the internodes, there are no channels in the membrane because the membrane is not exposed to the external environment or to the extracellular fluid. The only places that we see voltage-gated channels that are capable of propagating the action potential is in the exposed parts of the axon, which are known as the nodes of Ranvier. So these are the internodes, and these are the nodes of Ranvier. And the nodes of Ranvier are where we see the channels. Now, when an action potential begins at the axon hillock, the sodium from the local potential diffuses over and makes the membrane here more positive. That is what opens up, that change in voltage is what opens up these sodium channels, and now sodium can come into the axon. That sodium then diffuses. It diffuses this way, and it diffuses this way. This way nothing happens because the channels that are over here are resting, so they can't carry another action potential. But the sodium that diffuses over here makes this part of the membrane more positive. That opens up the voltage-gated sodium channels. Sodium comes in, and sodium again diffuses both directions. But when it goes to this direction, these channels won't open because they're resting, they're refractory. So only the sodium going this direction causes any sort of action, and that is to open these voltage-gated sodium channels. Sodium comes in, diffuses to the next node, sodium comes in, and diffuses to the next node, and so on. So if you were watching the action potential, if you could see the action potential as blips of light, for instance, then you would see a blip, 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 as opposed to an unmyelinated axon, which would just look like a wave of light traveling along. So in saltatory conduction, the action potential appears to jump from one node of Ranvier to the next, and that's how it gets its name.